So, good morning and welcome to this first appointment. Today we are talking about the Python application for oil and gas data to display and make analysis. Nice to meet you. My pleasure is, my name is Matteo, and this appointment is making a partnership with the Schlumberger Academy. So we are focused about pressure and porosity monitoring in clastic reservoir and carbonate reservoir. Estimate and plot clay volume, utility volume, plot volume of gas in different physical phase in clastic reservoir, analyze the composition in clastic reservoir in mixing zone, PVT calculation for gas clastic reservoir, create analytic tables for evaluate the incoming value for some companies. So for all kind of this point we are make example coding and analysis. So start for the first point, pressure and porosity monitoring in clastic and carbonate reservoir. What do you mean when we are talking about pressure and porosity, especially in clastic reservoirs? So we have three different type of porosity and condition. The interconnected porosity. This is a type of pore as then more one throat connected with other pores, and the extraction of hydrocarbon is related easy such in this kind of situation. The second situation in clastic reservoir is cooled sac or connected porosity. This type of pores has one thread connected with other pores of the hydrocarbon by expansion reservoir pressure. Closed or isolated pore. This type of pore is closed. It does not have a throat and connected with other more. So to yield hydrocarbons in a normal process. Generally, we have this table that resume the condition of also the diagenetic condition in which we have the process that involve the formation of gas in classic reservoir. For example, in shallow zone with temperature between this range, we have grain coating, non-pervasive carbonatic cementing. And in this situation we preserve the initial porosity. Other conditions that destroy porosity, for example, the clay infiltration, carbonate of silica, cement or autogenic catalytic will destroy the initial porosity. Intermediate, this kind of range of temperature is to medium state of this. In dissolved carbonate, so we have, for example, in barrier coralline in either zone, we have the preserve of initial porosity, destroyed porosity for kaolinite and this kind, feldspar carbonate, quartz cement, kaolinite precipitation. We can destroy also the porosity for high temperature. When we have high temperature, this minerals does not have a chemical phenomenon precipitation, and they can destroy this. Pressure and porosity monitoring, clastic reservoir, compactation, cementation, dissolution, and certain minerals can create, for example, in clastic reservoir, for example, in sandstone reservoir. This is the principal phenomenon and physical process that can be change the porosity along the life of reservoir. So the origin of porosity and the evolution, it depends on several parameters for example, the depth, the porosity, the origin of porosity, and they have also, for example, fracturing process that can be held to manipulate, to support to change not naturally the porosity of reservoir, but the chemical or physical process implemented by human hands. Generally, the natural porosity change with the natural phenomena like compactation and cementation, or the organic process like new clay matrix and leaking. So we can distinguish the primary porosity, that is the original porosity in the first sediment, and the second porosity when, for example, we have the compactation and the diagenic phenomena. It's clear that study and underline the history of clastic reservoir is more interesting and more important, also not all to understand the history and how is formed this kind of reservoir, but also to apply a new technique like machine learning technique to make a prevision of what will be the future evolution of reservoir, and how can change the porosity and also the different phase between water, gas, and oil. The constant compactation process that explain porosity loss increasing also in boreal sandstone and shale, while, for example, in shale we have the porosity that in some cases increase in time. So this is just an introduction to the problem of studying pressure and porosity in clastic reservoir to make easy to understand why we can use this kind of coding or an example. Why? Because today we are so most important to use, for example, machine learning technique to make a prevision around the evolution of porosity and pressure, and also to program the maintenance of reservoir. Degree of cementation or consolidation is we have different phase, for example, the clastic factor and air genetics and mesodiagenetics factors that can be analyzed in the first phase with different temperature of subsurface that can be also the temperature is more important to monitoring and to underline the evolution of reservoir. For example, we have deeper than 2000 meters, we can have a hot temperature change between 16 and 17 Celsius degree along the life of reservoir. We have a schematization of the different conditions through the experience and thanks also to the Schlumberger contribution, the different depositional phase and the typical diagenate alteration, and also the reservoir quality heterogeneity. For example, in zone we have a deltaic fluid dominated by different tide of oscillation of water and sea level. We can have this typical diagenetic alteration that conduct to generally a change at this behavior of permeability and quality of reservoir. For example, if you have in fluid dominated delta grain coating and or ideal free K, we generally have a permeability reduction. We have a chloroside coating preserve porosity during burial and initial quartz cementation along the life. Generally, in this kind of ambient, we have this behavior, so that it means permeability reduction and also loss in intergranular porosity. For shallow marine, for example, for depositional phase in shallow marine, we have the porosity of permeability reduction and strong vertically heterogeneity rate is strong. It means and also high quality of reservoir and also durability of reservoir. So I say all information because I understand that this presentation is focused on pipe coding, but I want to understand that all coding can be linked to the geological surface and the geological deposition, ambient and phases. Deep sea, for example, fan deep sea or fan deposit, strong heterogeneity related to formation of rather extensive cemented and strong, we have in this case different kind of porosity and permeability that can change in vertical or lateral porosity. And it's not too easy, for example, study, for example, in the fan deposit have a constant porosity. So we generally we use multiple well to capture gas. So problem is really complex. In today we are, for example, simulate a case in deltaic ambient, and we analyzed, as we just see, the primary porosity, that means the original porosity from deposition, just intergranular porosity, and the second porosity, that means the evolution of porosity of deposit after compactation and diagenetic performation. So typical value, for example, of clean sandstone and shale is this kind. So we have a pressure clastic in reservoir. These include more pore pressure that can be analyzed also for drilling safety and production for forecasting and reservoir compactation and subsidence risk. That is also more important. So analyze porosity not means only establish the capacity of reservoir or make only forecasting prevision about production, but it means also the condition for drilling safety and also the condition for not allow the subsidence risk. It's more important for the safety of all area. Relation between pressure and porosity. The normal compactation trend as depth increase, pressure and compactation increase, reducing porosity. Overpressured zone may occur due to rapid burial hydrocarbon generation or fluid expansion. In such zone, porosity may be abnormally high. So generally this porosity is very high, especially in this case for deltaic or is very high in the deltaic fan. How can measure the porosity is another challenging, because it's not too easy establish the linked correlation between the primary porosity and second porosity. We generally do directly in core analysis, but core analysis is like a photo, an instant photo. So to make the history effectively of the porosity is really interesting and really applying the log techniques, log geophysical techniques like neutron density and log sonic porosity. So the pressure, we have also the formation testing like RFT, MT, and the pore prediction for sonic from sonic and resistivity log, that are the most important techniques of log that can be used for the prediction. Implications, so high porosity with high pressure may indicate good reservoir quality and overpressure trap. If you have an overpressure trap, we can stay easy that we have a long stability condition. If you have a low porosity but high pressure may occur in the tagged sands or compacted shale, we can have an established reservoir condition. So you need really to monitoring to make safety drilling operation, but also safe drilling management of the area. Generally, we can follow also this scheme, underline this scheme, for example, to reconstruction the porosity, the history of porosity reservoir. If you first phases of analysis of during drilling evaluation and core analysis, you cannot see, for example, clay infiltration. You don't have oxidation, and so you don't have, for example, evaporite of this chemical precipitation. You can have a clear, a poor porosity, so we can don't have other diagenetic and chemical phenomena, so you have the preservation of primary porosity. And in this case, we can have a good porosity that respects the initial conditions. So probably we don't have a high change in porosity because you don't have the precipitation phenomena, chemical phenomena like cementation or like this, and you don't have the formation, for example, of evaporite. Pressure and porosity can be also following this scheme when we have in fluvial and deltaic ambient, we have a clean sandstone with the positional porosity of this percentage that is maintaining along the life. In marine facies, generally we have a strong reduction of porosity during the life, a compactation, a physical compactation, and also the formation of extensive quartz and carbonate cementation. Go to the code, make the first sample to analyze a matching data between the deltaic ambient with the grain coating ambient. So generally we can make this example for classic reservoir pressure and porosity, how can be also change along the next 5 years of starting production of reservoir. You can use this kind of code I will show you. You can import, for example, porosity port stream light to use to plot and show data. Constant, in this case, this data, initial porosity, initial pressure, and sidebar controls. We have simulated the porosity and pressure change prevision in next 5 years. So initial porosity, initial pressure, and we have also this kind. So I show you also in Streamlight. So it's clear if you go to maintenance and constant extraction, you have in this case a changing in pressure that it means tracked by this point, and also the changing in porosity that in this case remain essentially constant because we are in the positional phases of deltaic, so we have this parameter used, the initial porosity of 25%, initial pressure of this, and compactation rate and decline pressure. So we have we expect the analysis made with log and in clastic phase, and it's a good example of how used to monitoring how used to this code to monitoring clastic reservoir in deltaic phase. Pressure porosity monitoring in carbonate reservoir is critical for also for reservoir management and also to establish the enhanced oil recovery. That is important for all company for economical aspects, and also to planning all operation with about the maintenance of reservoir, the management of reservoir, and all kind of this. And also to prevent the damage of reservoir, or damage of reservoir, or for example, excessive compaction and subsidence risk in area. So we have some example of different techniques used to tomography 3D. Which is some best method that generally used to make this kind of analysis in carbonate reservoir. Density log, that is log can be generally also used make more 1 ounce time during the life of reservoir in carbonate reservoir, estimate the total porosity and how change the ratio between the matrix and the fluid density that are in reservoir. Neutral log sensitive to hydrogen content, used in combination with density to difference lithology, and sonic log estimate porosity using the wild time average equation. In sometimes also core analysis, but is not so recommended, but the best also we are NMR logs with differentiate between bound and free fluid porosity, useful in dual porosity system. Also we have pressure monitoring with MDT, FTT test, permanent knowledge gauge, production data analysis, interference pulse test, interpretation note, pressure drop, overpressure zone, fracture pressure analysis. Especially if you want to manipulate in artificial way the pressure and the porosity, generally we use fracking techniques, and it's clear that if you use fracking techniques, you need to make a strong planning of analyzes the ambient aspects, but also the seismic aspects and all kind of aspects that can be involved in fracking operation. Pressure and porosity monitoring. In this case, simulated logs, we are in this case we are show the coding that is involved in this kind of operation that can be supported by the also deal this kind of logs, for example density logs and neutral logs, that is more sensitive, for example also to hydrogen content. That is new challenge in geological exploration. And I show you the code and how can make the interpretation and how can be used in monitoring carbonate reservoir. Simulated log based on monitoring porosity and pressure in fractured carbonate reservoir. So in this case we are not need to to make other fracking operation. It's clear we are we are an interval of depth between 100, 2000 and 200, 8000 meters depth. We have the matrix porosity, the fracture porosity, and the total porosity. So we have two different type porosity, and the effective total porosity, that is the porosity that is represented effectively. The porosity is capable to make the flux of gas and oil. And so we have also the pressure profile that will be recorded during this interval of year, starting from 1995 to 2025. You can see that we have in this case we have a trend that is not underlined, is not good underlined, but we have a trend to increase the pressure, because it's clear when we make extraction for a long period we can have also the compactation and other diagenetic phenomena. So that means that we make attention for not only for the subsurface phenomena, but also for the surface phenomena, for subsidential phenomena. We can download easy in this case the data, depth, total porosity, air pressure, and we can distinguish different zones. So is an example of this kind of application. Go next to the estimate. Second point, estimate and plot clay volume and total porosity. As we just understand, in some phenomena, in some case, we are not able to preserve the original porosity, but we have also the phenomena of clay infiltration. Clay infiltration is a geological phenomenon that can be evolved in formation of oxide and evaporite. So in this case, when we have the clay infiltration, the total porosity can change extremely. So as we just say, it's clear that underline and talking about the porosity, it means different kind of concept, because we have the porosity in geological concept, that it means primary porosity and secondary porosity, as we just underlined, intergranular or valves or fracture, but for engineering application, we generally use total porosity, that it means effective porosity and ineffective porosity. The total porosity is generally good estimated by neutral log and density log. Is the common log techniques used to make this kind of analysis. But first, to do this, when we make, for example, the total to do the total porosity estimation, when we are doing the neutral log or density log, it's clear to underline and to understand the clay volume that is infiltrated in for example, in sandstone, in sand or tar sands sediments. So to calculate the clay volume and all kind of mineral that caused, for example, diagenetic phenomena like chlorite, mineralization, oxide, and other kind of this, we can use this kind of formula that is based to gamma ray logs. That is really essential to reconstruction the history of reservoir, and also to make the prevision of about the Volvo reservoir, and also to calculate the true porosity, total porosity. The true porosity can be used, for example, the neutron log porosity, the methods of determining neutral density porosity is this for gas bearing formation. The correct neutron dense porosity, we have the original neutron dense, and after you connect for a value of sigma value. Here we can show an example of code and how can be affected link to neutron porosity log and neutron porosity section. So it's clear when we make also the neutron porosity, you are really studying in details the porosity and the density. And when you are studying also porosity and especially density, it's clear you can make like a photograph also of different phase of different physical phase that we can behave in reservoir. If you have, for example, liquid phase, gas phase, and condensate phase. It's really essential to understand and planning all future aspect of drilling engineering in reservoir. So we have a low porosity, liquid and gas. I show you the code. Clay volume and effective porosity in classic reservoir. From gamma ray log, we can have the estimated of clay volume and calculate the utility volume using for total porosity, and also if you have the total porosity, you can estimate how many feet cube or meters cube of gas we have effectively in your reservoir. Clay volume depth, this is a plot of clay volume versus depth, so it's not a pure reservoir, it's a reservoir that have a complex evolution, the genetic evolution, because we have a high quantity of precipitated clay, and so we have is linked corresponded to also the depth porosity that it degrees in depth. So we have a grid porosity in this range of depth. Here we have a table overview between depth, gamma ray, total porosity, clay volume, effective porosity, and depth, gamma ray, total porosity, clay volume, effective porosity. So starting from the value of gamma ray API, we can estimate the total porosity and also the volume of clay for the different depth, range of depth. And the effective porosity, that is the value most important. As we just underlined, we have an decrease in depth. The measured value is in this value, in this interval. Okay, it's a good example to a not so property classic reservoir. In this case, we have probably analyzed a shallow marine shore face deposit. A shore face deposit. Point 3, example 3, we are plot volume of gas in different physical phase in plastic reservoir. So go on and follow the previous line. When we are make this petrophysical analysis, this kind of logs analysis, especially the neutron porosity log, neutron density porosity, we can underline also the different physical phase in reservoir. If you have only liquids, gas condensate, and planning all the future operation. What does it mean? It means to make a geological reconstruction of the area. It means also to understand the process that we are starting for the first time, the pre-production. There is water, oil, fault, barrier, oil, which can be the scenarios, can be evolved the situation, because in this case we have a deltaic. We have this. We are in this depositional phase. We are in fan deep sea, in deep sea, fan deposit. We can have a shale gas, but we can have also sand gas, and we are not a unique reservoir. We are a spotted reservoir in this case. So we can have different scenarios. It can be evolved condition reservoir, but can be evolved also the gas. Can be changed the volume of gas, and because we have 3 different phases: liquid, gas, and condensate. So we have to manage a complex physical situation. In this case, we have a gas X solution, or we can have, for example, also the phenomena of repressurization. Because why we need the repressurization? We need the repressurization to manage attentionally this part, because when we have condensate and gas, we can corrupt the trap. So the best situation is to control the pressure and make all condensate. It's too easy. So in this case we want to repressurization the reservoir. A typical production profile under solution gas is this. For primary gas cap we have this situation, gas but also water, and we can be also an evolution in mixed phase, gas, oil, water, with intergranular residual oil. It's clear that can be you need to control is a real case extracted by Schlumberger database. You need to control the pressure and to transform all gas vapor gas in condensate phase. So in some classic reservoir we can have also the inverse phenomenon. The oil can be evolving gas reservoir. And finally we have this kind of situation by changing in pressure and temperature. When pressure and temperature change, for example, we have an increase of pressure and decrease of temperature, we can transform some parts, some molecules in gas. Here is the code example, really example code. This model is simulated reservoir fluid evolution, the pressure decline. So in this case we have a pressure decline. So is not referred to the first case is more complex, because in this case we need the repressurization. We have a simplified example linked to the oil reservoir, principal oil reservoir, that can be evolved in this case with we have a volatile part, can be evolved also in gas. And so this model is simulated the reservoir fluid evolution, pressure decline, and recovery factor from an oil reservoir transition to gas over 10 years. Go to example. Okay, you see the sample, you see the plot in this case of the sample you show is that linked for oil and gas and water volumes over time, how we change. We have water change, water is constant, the gas in this case decrease, so because we have and we have now an increase of oil. Last 2 points, analyze composition in classic reservoir zone. We can do analyze composition in classic reservoir, for example, capillary pressure, transition zone, and gas gap or GOC, and also the other physical parameters like diffusion, gravity, segregation, wettability or capillability and pressure. It's so clear when we have a fine deltaic deposit, we have a complex situation, a really complex situation about the pressure and porosity, but we have also to need to study and to underline other parameters like diffusion, gravity segregation, wettability, and capillarity and anti-pressure difference, because to improve and to use all potential of a reservoir, you need to study all this kind of parameters. What can analyze and simulate? So we need to analyze these parameters: water, oil and gas saturation mixing zone, because generally we have always a mixing zone in this situation. With a standard lithology, we have a column of clay, of marine clay. The evolution of area is representing it in this way. And generally we have also the presence, when we have this, in this first case, the primary porosity was trapped by the genetic phenomena like sandy dolomite or sandy dolomite, or for example evaporite deposit. And after we have the good characteristic for proximal channel. In the proximal channel we generally find the reservoir, some gas reservoir. So, but we have a mixed phase because we have water, oil and gas mixing zone. capillary pressure versus saturation, and also we have a fluid composition variation, API, gravity, Gore salinity, and we have also resistivity and saturation. And the transition, we have also to analyze the thickness of transition zone. Is a typical cross section with Miocene up later Pleistocene section of this area. Oil and water is located. We have a gas condensate reservoir here, so we have a different phase as we just underlined, and continues to the previous example. We have different phase: gas condensate reservoir, oil reservoir, and oil and water here. Complex situation. We have to isolated the different part of reservoir using different drilling techniques and different extraction techniques. Analyze composition in plastic reservoir in mixing zone. Example coding in this case. The model is based on electrical logs. Electrical logs and petrophysical interpretation can really support this kind of analysis and these kinds of evaluation. For example, we have the porosity, the true resistivity, the formation water resistivity, and you compare pressure gradients and other kind of this. Analyze composition. We have an example code that include also plotting viscosity, density, bubble, and all parameters we are in this checklist. So for the water, oil and gas, the value of saturation of gas, the value of saturation of water in the mixed zone, and the contact depth. I try to show you. Classic reservoir composition and analysis in mixing zone. So we are mixing zone, we are in this zone, we are around this depth, we are talking about this part in proximal channel. We have a fluid compositional change, capillary pressure, lab oil brine curve, and we have also the gas saturation zone and compositional change. The capillary pressure in this case remain constant, and also the water saturation. That means that the reservoir is like a stunned, separated. We have some geological fault, for example, also phase that make separation between. So is a pressurized reservoir in this case. That is a good condition. Gas saturation in GOK zone, underline that we have an increase of gas saturation around this range of depth. So that means that the major part of gas is contained in this range of depth. So probably here we have condensate gas reservoir, and here we have a trap, also trap, and an alternance, because as just to say, we are in this geological context. A wireline log resistivity density neutron. In this case, the neutron log show that density and resistivity remain substantial constant. Eos factor fluid, how can change the fluid and the pressure of fluid. The fluid change, we have an increase of pressure fluid, but is moderate increase. And so we have also the resume table with all value. Okay, go to the point 5, PVT calculation for plastic reservoir. Why it means PVT and why we need PVT. PVT is a mass balance and is key equation in simulation to simulate it also the solution, the gas. When we have, for example, a not separated phase, when we have a gas solution in oil, we need to calculate this ratio, gas-oil ratio, gas solution ratio. We have also to enhance the oil viscosity and the oil formation factor. Where does PVT comes from? Laboratory experiments, or is also used in some correlation in software like Petrel. We need also clear to do the a sampling of fluid of reservoir to make a fluid analysis. The black oil model is based on sample interpolation of PVT. We have this phase, aqueous phase, liquid phase, and vapor phase. Composition simulational models are needed in the following case: when we have gas oil, or when we have, for example, gas oil water. And to underline also the surface separation and the gas plant calculation. Types: bottom or hole sampling, wireline DTS sampling and production wells. Surface sampling, for example, when we need to make a sampling in surface, for separating separator sampling. We can sampling, for example, also the water, but we have also the fluid characterization with MDT, RDT. The key parameters that we can underline is the following: is the gas compressibility factor, the gas formation factor, and the gas density. So it's clear that is a physical approach, because we can need to understand the isothermal compressibility of gas, the gas derivation from ideality. And to do this kind of model, we are using this workflow. For example, reservoir temperature, initial reservoir temperature, the pressure, the gas specific gravity, the gas composition, the depth of pressure gradient, and also we have calculation of zeta factor using this equation. Go fast and I see you the code, because this part is a really technical physical engineering part for gas reservoir. I show you the code. So in this case we are calculating the PVT properties, the pressure, volume, temperature properties of gas classic reservoir. We can editable parameters like gas specific gravity. We are put a standard value. Temperature is too high. Can consider this. Pressure in atmosphere. And so we have also this kind of result for this simulation. In this kind, with using these input parameters, gas specific gravity, temperature and pressure reservoir. This is the physical parameters of reservoir, temperature and pressure recorded in reservoir. We have the zeta factor, the formation volume factor and gas density that is expressed in mole ratio liters. So that it means in this case for 1 mole for 0.4 mole of gas we have 1 liter. And gas viscosity, that is also an estimation if how the gas is compacted or condensated. The zeta factor with pressure, in this case we have the zeta factor and increase of pressure, so is a pressurized reservoir. We have a pressurized reservoir, but is not condensate because the gas density is too low. Is a pressurized reservoir, but gas is not probably condensate. And gas density with pressure that underline the same phenomenon that in this case you have an increase of pressure with an increase of density, but the change of density is too small. Last point that I think is the most interesting for all other companies that that not make service like Schlumberger, but for other committed company is make analytic tables for incoming by the gas, by the cell of gas, and so make prevision of production rate and gas. So I think is the most important, is the most interesting last point for all other company that we are not make service like Schlumberger. So initial gas, what we can use in this model to simulate, we have finally arrived to the point. We have make the all analysis, we have find the gas, we have an estimation that are pressured reservoir, so we have all petrophysical parameters checked. The situation is clear. We need an economical analysis of investment. So in this case, you need to gas production rate in million cubic feet, the time period in years, and also an estimation of price fluctuation. We can consider around 10 or 5 years, dollars per year. Air gas fluctuation is modeled around the initial price. Revenue per year is calculated as revenue gas price per production rate per year duration. Output, we can output this kind of output table showing the yearly revenue, plot showing how the price is affected by fluctuation of revenue per years. And so we have this kind of inputs: initial gas price, that is the price that today or tomorrow we are bring at Wall Street or Nasdaq in our this part. Gas production rate, for this case we have just an idea of the gas production rate because we have analyzed all parameters, and number of days, the times spent to the simulation. In this case we can use 5 years, but we can also change. Price fluctuation. The price fluctuation is modeled using random variation in the price within the range of $5 per year. We have also the incoming, the revenue calculation. Here revenue is calculated as the product of gas price, production rate in 3, 6, 5 days by years. This result is called $2 million. So go to simulation to view how can change. Is like a machine learning simulation, the prevision simulation, how gas price can change over time and which will be the incoming. Okay, we have editable parameters that can be adapted to the situation of tomorrow, to 1 week, or to 1 year situation. We have initial gas price that I think now is too low, is too high because it's simulated now. Yeah, it's too high. So we can consider $20. A gas production rate we can increase in this case. Gas production rate is by year. Okay, number of years, we can consider 5 years, and we have this kind of situation. For the first year, we have a yearly revenue of this value in million USA. For the second year, we have this value in revenue of million USA, and for third year, so we have just the best a prevision of high production between the second and third year in this case, with start decreasing from the 4 year and the 5 year. We have a drastic decrease of production and also to the revenue. So the best the production is very highly in second and third year. So we are make a prevision that the gas price in this situation, in this economical and geopolitical situation, gas price remain constant, essentially constant with small oscillation. So we have the easy calculation, the revenue for the committed company. Okay, It was for me a really pleasure to make this kind of presentation. I think it will be interesting with much more application. And thanks for attention. For course or other information, you can contact me by mail. This is my mail, jexplorationuk@gmail.com. Thanks for attention.